Okay, welcome to lecture. We're going to continue on to chapter 3. All right, so we're off to chapter 3. Again, please type that you're here in the chat box there for roll. All right, so remember that this here is not going to be on our first exam. So this is starting the material that will be on our second exam. I know, again, on excuse me, on the first exam, it does cover chapter 3, again from chapter 3. Really, the only thing that you need to know about is electronegativity, what it is, the general trend, to go along with the other trends that we talked about in chapter 2. So we're going to talk about electronegativity again in this chapter, but what we talked about it in terms of the previous chapter is really all that you sort of need to know for the first exam. And again, the rest of it you'll need to know, obviously, for the second exam. So we're going to get into bonding now. We're going to talk about in this chapter Lewis structures, chemical bonding, the different types of bonding, both ionic bonding and covalent bonding. And then we'll get into, in the next chapter after that, some of the geometry, hybridization and stuff like that. So next couple of chapters obviously linked together, chapter 3 and chapter 4. Chapter 3 kind of drawing everything in terms of Lewis structures. Chapter 4 getting into all the geometry and polarity and all that kind of stuff that kind of go together. All right, so let's talk about covalent bonding, or just bonding in general here. So first off, when we do bonding, we usually oftentimes represent bonding with Lewis dot symbols. Lewis dot symbols are also sometimes called electron dot symbols. And as we will see, they're basically a symbol. So we use the chemical symbol, and we use one dot to represent each of the valence electrons that are in the particular atom. So one important thing is when we talk about sort of bonding, it's all about really the valence electrons. So we talked about valence electrons last time. And again, the valence electrons are those highest in energy. They are the electrons that are furthest away from the nucleus. So as we talked about with those trends, they're not going to be held as tightly. And again, that's why they're really involved in bonding. They're out there furthest away from the nucleus, not held as tightly. They're able to be either gained or lost, or also shared. So if you think about bonding, think about electrons. Electrons are on the outside of the atom. So when two atoms come together, they're really the first things that sort of come in contact with each other. And again, it results in the two types of bonding that we will see in this chapter: ionic bonding and covalent bonding. So as I mentioned, to show Lewis structures, or Lewis dot symbols, and again, sometimes called electron dot symbols, we use a dot to represent each of the valence electrons. We also talked about that pretty much it is easy to figure out the number of valence electrons. They are equal to the group number, right? So the number of valence electrons equals the group number on the periodic table. So everybody in group 1 has 1 valence electron, everybody in group 2 has 2, and so forth, all the way through group number 8. And usually we're talking about the representative elements, so our 1 through 8. Again, the transition metals, you really won't be drawing anything that involves transition metals, so you don't really have to worry about valence electrons in terms of transition metals. So as I mentioned, it pretty much consists of a dot and, again, the actual elemental symbol. And as you can see here, it looks just like this for each of the guys here. So everybody in group 1 has 1 valence electron, so they all have 1 dot. That includes hydrogen as well, that has only 1 electron total. group 2, 3, 4, 5, 6, 7, 8. There's really no sort of rule in terms of Lewis dot symbols or electron dot symbols, but basically we use the symbol. Really the only main rule is there's no more than 2 electrons per side. And usually most people will kind of go around and kind of clockwise and put one at a time and then go back and kind of fill them up. But really there's no true rule on that. The real main rule, as I just mentioned, is just not more than 2 per side. As you can see, if we look at 2 per side, there's 4 sides. That means our elements are going to max out at 8 electrons. And 8 is an important number. It is also the same number of valence electrons as our noble gases here, right? And as we'll talk about, that is essentially really the basis of all bonding. Is everybody is trying to get to the noble gas configuration. They're all trying to achieve that same electron configuration as the noble gases. Remember, the noble gases are chemically inert. They're extremely stable. And basically, that is what everybody's trying to achieve. And they're through the 2 types of bonding, they can achieve that either through gaining and losing electrons, which is how it happens in an ionic bond, or they can sort of gain that situation through sharing of electrons, which is what happens in a covalent bond. So again, like you can see here on this little picture, you're not going to really come across anything that you need to draw in terms of transition metals. You don't have to worry about valence electrons. In terms of valence electrons and transition metals, you know, some people will say that they have 2 valence electrons because, as we talked about last time, when those transition metals start to lose electrons, it's those s electrons that get lost first, and there's only 2 electrons in the s, so some people will say they have 2 valence electrons. Some people could say they could have upwards of 12 with the, 2 that are here and like the 10 that are here as well. So, you know, again, you don't have to worry about, I'll spit that out, I think, worry about it. In terms of Lewis structures, but that's sort of the common sort of answer, I guess, for transition metals. They could have upwards of 12, depending on which one you're talking about, but some will just usually talk about them in terms of 2, which is those s electrons. So let's talk a little bit about Lewis structures or Lewis dot symbols and what they sort of help us sort of understand. And it's really the 2 types of bonding. So the 2 types of bonding that we're going to talk about is really ionic bonding and covalent bonding. And ionic bonding is pretty much between a metal and a non-metal. And what happens in an ionic bond, as we will see, is basically there's a transfer of electrons. So we get this transfer of electrons that occur from the metal to the nonmetal. And as we talked about earlier, when a metal loses electrons, because of all those periodic trends we talked about, he's going to become a cation, which is positively charged. And when the nonmetal gains those electrons, he's going to become an anion, which is negatively charged. And it is that attraction between those 2, which is sometimes referred to as the electrostatic attraction, that opposites attract. The positive and negative attraction is what holds that together. So as we'll talk about here, there's absolutely no sharing of electrons in an ionic compound, and that's really important. And that's the major difference between that and a covalent compound, or sometimes referred to as a molecular compound. In a covalent compound, we're pretty much taking 2 nonmetals. And the major difference is here we have sharing of electrons. And as we'll talk about in this chapter as well, that sharing of electrons may be equal sharing of electrons, which creates what's known as a polar covalent bond, or that sharing of electrons may be unequal, which creates a nonpolar covalent bond. So there's some aspect of sharing going on in a covalent compound or a covalent bond. And that's, again, very different than an ionic bond where there's absolutely no sharing of electron that's basically happening. So when we talk about sort of ionic bonds, which we're going to focus in on first here in this chapter, Ionic bonds, as we talked about, cations typically will have those low ionization energy. So a reminder that ionization energy is the energy required to remove an electron from an atom. And when we obviously remove an electron, it becomes positively charged or a cation. And if you have low ionization energy, that means you do not have to take a lot of energy to actually remove the electron. And that's opposite from our guys that typically will form anions, those guys upper right of the periodic table. Those guys have high negative electron affinity. And if you remember, electron affinity is essentially what we look at when something gains an electron. And things with high electron affinity means that they're more apt to basically gain electrons. And when they do, they would become negatively charged and become an anion. So a lot of those periodic trends, as we talked about last time, have a big role in what we see in terms of the elements. Metals typically, again, wanting to sort of give away their electrons and not really hold on to them. Non-metals typically want to hold on to their electrons and actually would like to actually gain some more electrons. So the general rule sort of tells us that elements likely to form cations are group 1 and 2. Those likely to form anions, again, are halogens, which is group 7, oxygen, nitrogen in that particular case as well. So let's take a look at an ionic compound coming together. Our lithium and our fluoride are to make lithium fluoride. So lithium, which is group 1, and fluorine, which is group number 7. So if we were to draw the Lewis dot symbols for each of these guys here, they would look something like what we see here on the bottom. So we have lithium, which is group 1, has 1 dot. We have fluorine, which is group number 7, it has 7 dots around it. And again, because this is a metal and a non-metal, what's going to happen in this particular case, and when we look at our electron configuration for each of these guys, the electron here in the lithium is going to go around the corner here and transfer over to the fluorine. And when it does so, a couple of things happen. We get lithium here, and let's redraw it over here, that ends up having a positive charge. We get the fluorine, which basically picked up that electron. And because he picked up the electron, he now has a negative charge. And this is really the way you should draw ionic compounds when you're using Lewis dot symbols or electron dot symbols. A couple of important things to see there. They both have charges. And there the lithium becomes positively charged like we would expect. The fluorine becomes negatively charged like we would expect as well. And we do need to include the charges when we draw these symbols. And that indicates to people that the electrons are not being shared in this particular case. You'll also see, kind of like what I drew there on the right-hand side, that sometimes people will put brackets around one of the ions there just to also indicate that there is no sharing of electrons happening here. So what we have is essentially a full transfer of electrons from our lithium, which is our metal, to our fluorine, which is our non-metal. Now, what happens in terms of electron configuration? Well, the lithium here is going to transfer its valence electron, which is here. This is its 1 valence electron. So when it transfers its 1 valence electron, the lithium on this side, excuse me, ends up as 1s2, which is the same electron configuration if you look on the periodic table for helium. And again, lithium here has now achieved the same electron configuration as helium. Remember, things with the same electron configuration are what are referred to as being isoelectronic with each other. When we think about the fluorine here, it's got room right here in this subshell to basically pick up that electron. And it does pick up that electron coming in from the fluorine, from lithium. And it ends up with an electron configuration of 1s2, 2s2, 2p6. And again, that is 10 on the periodic table. So that also means that fluorine has now achieved the same electron configuration as neon. So fluoride, which is the minus charge there of fluorine, now has the same electron configuration, are isoelectronic with neon. And the overall sort of goal here for both of these guys have been met. They have both now reached the noble gas configuration, which again is basically what everybody's trying to achieve. And now they both have basically achieved that. Again, lithium achieves it by losing an electron, and fluorine achieves it by gaining that electron. So what holds that whole unit together is that opposites attract, that electrostatic attraction, that positive negative attraction between the two charges here. Again, absolutely no sharing of electrons happening here in our ionic bond. Any questions on that there? So as I mentioned, that unit is held together by no sharing of electrons, but again, that electrostatic attraction between the cation's positive charge and the anion's negative charge. And as I think we talked about a little bit as well, the strength of those type of charges, for example, when you put a +3 and a -3 together, that's going to be held a lot tighter than a +1 and a -1. So as the charges sort of increase, so does the strength of that attraction between the two ions when they come together. We also sort of saw this when we're talking about electron configuration for our representative element. Remember that essentially our metals on the periodic table, when an ionic compound sort of happens, they will back up to the noble gas that comes right before them on the periodic table when they lose those electrons. And our nonmetals actually go the other way. Our nonmetals on the periodic table, when they gain electrons, they go forward to the noble gas that comes after them. So if you look on the periodic table, again, behind lithium will be helium, which is why it backed up to helium. And if you look on the periodic table there, in front of fluorine will be neon, so it goes forward to reach that noble gas configuration. So let's take a look at another example. If we put calcium and oxygen together. So if we put calcium and oxygen together, calcium is group number 2, so it should have 2 valence electrons. So our Lewis dot symbol is there on the left. Oxygen, which is group number 6, has its 6 valence electrons, which is also on the left there. And again, if we look at our configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That 4s2 is the 2 valence electrons that we see in calcium. And if we look at oxygen's electron configuration there, oxygen's electron configuration, which is number 8 on the periodic table. Sorry, I just kind of move something around there. There we go. Which is going to give us 1s2, 2s2, and 2p4. If I did the math there, 4 and 4, there goes 8. And the 6 valence electrons there in oxygen are right here. They are the ones on the second energy level. So what's going to happen in order for calcium to get to that noble gas configuration, it needs to lose not one of these electrons, but actually 2. So for example, one comes here, the other one goes around the corner in this case and comes over here. And what ends up happening in this particular case is the calcium, which loses both of its electrons, now becomes positively charged on this side. So again, we have our calcium that becomes positively charged. Our oxygen gains those 2 electrons and also gains a -2 charge as well, again, from the 2 electrons that it gained. And again, it's that attraction between the positively charged calcium, in this case, or cation, and the negatively charged anion, which is our oxygen here, our oxide, which has a -2 charge. So what happens again in terms of electron configuration? Our calcium, which loses its 2 valence electrons there, goes from 20 to 18, which means when it loses those 2 electrons, it has now been able to achieve argon's configuration, which makes it very happy. It now has the noble gas configuration. The oxygen here in the P subshell has room for 2 more electrons, so it'll pick up those 2 electrons and become 1s2, 2s2, 2p6, and that's going to give us 10, and the oxygen is able to achieve the same electron configuration as neon. So again, in this case, they both are able to achieve that noble gas configuration by gaining and losing electrons in this case. And again, that's a very stable sort of situation. Any questions on that there? So before we talk about covalent bonds, let's actually talk about what would happen, for example, and this will also sort of explain later on when we talk about nomenclature and writing chemical formulas, you know, sort of what happens and why we do certain things. So what happens if we take calcium, which we have in this particular problem here, and we put it together with the fluorine that we had in the first problem? So if we take our calcium again going to have our 2 valence electrons. And if we put it together with our fluorine, which is group number 7 on the periodic table, we'll have 7 valence electrons. And again here, when we do this, the calcium really does need to lose 2 electrons. So he's going to take his first electron here, and he's going to put it into our fluorine here. This now creates sort of a problem, as you hopefully could visualize. When that fluorine gains that 1 electron, it's pretty much done. It now has 8 electrons on it, which is good for the fluorine, but not so good for the calcium, because now calcium, if it only lost, for example, if you look on the periodic table, if it only lost the 1 electron, it's pretty much only going to back up 1 space, and that's only going to take it to potassium. And that definitely, potassium is not a noble gas, so it's not going to be able to reach that noble gas configuration by losing only 1 electron. So again, calcium does want to lose 1 more electron so that it can back up to argon, which would be the next guy that would come on the periodic table. So obviously we can't do that with just the 1 fluorine. So in this particular case, we don't need just 1 fluorine, but we actually need 2 fluorines here to do this. So we would actually need another fluorine. And this fluorine now has room for calcium's 2nd electron that needs to be lost. And what ends up happening is all those guys, we now have our calcium that has a +2 charge. He was able to get rid of 1 electron to each of the fluorines. Each of the fluorines there picks up 1 electron and becomes negatively charged. And we would have another fluorine that picked up 1 electron and become negatively charged. And absolutely none of those guys are sharing electrons. It's that attraction between the minus charge in each of those fluorines, are fluoride guys, and the calcium's positive charge that holds that together. And that's why, perhaps if you remember when you talked about nomenclature, perhaps in the previous class, when you write a formula for an ionic compound, you need to balance out the charge. So the correct formula for calcium fluoride is CaF2. And that's because we have 1 calcium at +2 and 2 of these fluorides at -1. That gives us -2 and +2. Everything is balanced when we write the chemical formula. So always when we write a chemical formula for an ionic compound, we want to balance out the charges, the positive and negative, to make sure that we end up with no charge overall. And this is really the reason why you have to do that. The reason why you have to do that is if you did not balance out, say, calcium and fluorine here, and you just wrote CAF, calcium would be stuck there at potassium and really not be able to achieve that noble gas configuration. So really the reason why we balance out everybody in terms of their charge when we write an ionic compounds formula is really for this reason here. That allows everybody in that ionic compound to basically achieve the noble gas configuration, which, by the way, if we look at this one, I'll change the color maybe here, just so we're clear. Everybody here has achieved the noble gas configuration. Calcium lost 2 electrons, which means calcium at this point has the same electron configuration as argon. And each of the fluorines gained an electron, which means this guy up here ended up at neon configuration, and this guy here ended up at neon's configuration as well. So all 3 of those guys were able to achieve noble gas configuration, again, by gaining and losing electrons, which is really what happens in an ionic compound. Absolutely no sharing of electrons happening there, just that positive negative attraction. Any questions on ionic compounds, how to draw them in Lewis structures, what's going on with their electron configuration? Again, if you have any questions, feel free to type them into the chat box or anything like that. Okay, so now that we talked about sort of ionic compounds and ionic bonding, which is what we have been talking about up until this point, again, no sharing of electrons, transferring of electrons, we're now going to talk about covalent bonding. And ionic bonding, as we talked about, is really between a metal and a non-metal. So pretty much if you see that combination, metal and non-metal, it should automatically ring in your head. That's like an ionic compound. That's no sharing of electrons. That's transferring of electrons. Now, the difference to that is the next type of bonding, which is, again, what is referred to as covalent bonding. And covalent bonding typically occurs with, as I mentioned, 2 nonmetals. So 2 nonmetals come together. And what happens when 2 nonmetals actually come together, it has a lot to do with basically those periodic trends that we talked about. If you think about where the nonmetals are on the periodic table, all those nonmetals, right, are on that periodic table above that staircase, right? And above that staircase on the periodic table where we find those nonmetals, what that means is they are all pretty much in the same location, which means they all pretty much have very similar periodic trends, things like electronegativity, things like ionization energy, and so forth. And what happens when 2 of these guys get together, really the best that you could do is they agree upon kind of sharing their electrons. They're like, I want to hold on to my electrons. I want to hold on to my electrons. So the best they could do is basically kind of just agree to sort of share those electrons so we don't get a transfer of electrons like we see in an ionic compound where, just for exaggeration purposes, I'll draw metals over here. We have metals on the way opposite end, right, of the periodic table. And what that means is when a metal and a non-metal come together, they have very, very different periodic trends and sort of those properties. And again, as we talked about, the metals are like, go ahead, take my electrons. I'm not really interested in hanging on to them. While the non-metals are like, cool, thanks. I would like electrons. I want to pick them up and all that kind of stuff. So when we do get into covalent bonding, because everybody is pretty much in a similar location, for example, on the periodic table, they all share similar sort of properties, and the best they can do is sort of agree upon sharing of electrons. And as we will see, that sharing of electrons may be like equal sharing of electrons. They both agree to kind of equally share it. Or there, you know, there's going to be situations where one atom will go, I want those electrons a little bit more than the other, but they'll still be sharing it. There's some aspects of sharing, but it'll be some unequal sharing. So Lewis, hence who we named Lewis structures after, came up with the idea of bonding as basically the sharing of electrons that occur when two sort of atoms come together. So here we have our hydrogen, each has one valence electron. Again, obviously they have the exact same chemical properties, or periodic trend type properties. So what's going to happen is obviously they're going to share those electrons. And we can represent it as we see here, one of two ways. We could represent it with the two dots that are here. Or again, as like it shows on the bottom, we can represent a covalent bond with a line between the two atoms. One line represents two dots, and obviously the two dots represent two electrons. So one line represents one electron pair. And really, by sharing these electrons, these nonmetals are able to achieve pretty much the exact same thing as our metal and nonmetals are able to achieve by transferring electrons. So if we look at hydrogen, the two electrons here on the right-hand side for this guy on the right, hydrogen, count for it. But because those electrons are being shared, the guy on the left also gets to share those two electrons. And that's important because what that essentially does is get hydrogen to two electrons each through sharing of electrons. And again, if you look on the periodic table, the element that comes right after hydrogen is helium. And this is a really important thing to also remember as we're talking about covalent bonding. Hydrogen only needs two electrons to be happy. Hydrogen should never have any more than two electrons when it's in a bond. So I'll put a bunch of arrows around it. That means you shouldn't be drawing a bunch of dots around hydrogen, 2, 3 bonds to hydrogen. Hydrogen should never find itself in the middle. It should always be on the outside. Again, hydrogen just needs to go one step forward on the periodic table to reach helium and also reach that noble gas configuration. So really, really important to keep in mind. And for some reason, people always like to put a ton of electrons on hydrogen when they're drawing Lewis structures and stuff like that. So hydrogen really only needs two, as we'll talk about in this chapter. Pretty much everybody else wants to get to the noble gases, which is 8 electrons. So, in a covalent bond, basically what happens is we have these electrons that are between the two atoms, and they are being shared. And remember that there is that positive charge of like the nucleus. So for example, in our hydrogen, just exaggerate, draw it here a little bit far from each other just to kind of show it. You could kind of envision, right, that there is like the positive nucleus sort of here and here. And again, these electrons here, I'll just draw it like this. They're going to feel an attraction, obviously, to the nucleus and the hydrogen on the left. They would obviously feel an attraction to the nucleus there on the right. And that's essentially what locks everybody into place, right? So the electrons kind of feel an attraction this way, but yet they feel an attraction this way. And that sort of locks them into place between the two atoms. Is sort of that mutual attraction. And as we'll talk about in this chapter as well, and as I mentioned before, sometimes the attraction is a little bit more one way versus the other, depending on what elements you have sort of involved. So let's take a look at F2, and the electron configuration for F2 there is 1s2, 2s2, 2p5 in this case. Now, when these two fluorines come together, again, obviously they are identical to each other, which means that they obviously share identical properties. So again, they're not going to transfer electrons, but what's going to happen is these two electrons sort of in the middle here are going to be shared. And when they do, we get one of two structures. You can either draw it like the one on the left there, where you show dots all the way around, including the dots involved in the bonding. Or to represent that bonding, you could just use that line there to represent the two electrons. But regardless of what you do, the fluorine on the left there counts those electrons in the middle, while the fluorine on the right also will count those electrons there on the middle. And what that means is both fluorines in this case have, if you count them, 8 valence electrons around it. That obviously means that they have now basically achieved the same electron configuration as the noble gases. And again, they're very happy in that situation when they do that. Now, when we do look at this Lewis structure a little bit closer, there are really two types of electrons that we see here, and where all these claws are, all these dots that are here. These are what are referred to as non-bonding electrons. As you can see, there's no other atom or element there on the other side of them, which means they're not involved in bonding, so they do have that creative name of non-bonding electrons. If you're old like me, and a lot of people still call non-bonding electrons lone pairs, and I probably will as well. So if I say lone pairs, it just means non-bonding electrons. It's basically the same thing. So it's kind of an older name that used to be used or still used a lot as well. But lone pairs and non-bonding electrons mean basically the same thing. There are electrons that are not involved in bonding. So obviously we do have electrons involved in bonding, otherwise we would not have a bond. And those are the electrons that we find right here in the middle. Actually, write the pin the right way, that would work better. And since those electrons are involved in bonding, they do have a very creative name. They are known as bonding electrons. Yeah. So bonding electrons, much like the name implies, are electrons involved in a bond between two atoms, while lone pairs or non-bonding electrons are ones that are not involved in bonding. When you do draw these Lewis structures, it's important to show all of those things, to show both the bonding and the non-bonding electrons in your picture. So when you draw Lewis structures, you should always show both the bonding electrons, and it's really the bonding electrons that you have a choice. You can either show it as a line, like we do in this picture, or you could use dots as well, which is perfectly fine. But our non-bonding electrons, again, typically shown as dots, and you do need to make sure that you include both of those in every picture that you draw. That's a Lewis structure. So a Lewis structure, as we've sort of seen here, is really a representation of covalent bonding, where we use those Lewis dot symbols to show sharing of electrons that are occurring. And again, it's those sharing of electrons that can be represented by either the dots or the lines when you do that. It's also important to keep in mind, as we talked about at the onset here of this lecture, that we are only really dealing with valence electrons in each of these atoms, and those are really the only ones that are shown in Lewis structures. It's important to remember that obviously there are more electrons there, those core electrons, which we'd also talked about last time, which are closer to the nucleus, not involved in bonding. So each of these elements obviously still have those other electrons, those core electrons, but again, because they are not involved in bonding, we don't include them or really worry about them in terms of Lewis structures. So for example, our oxygen that we saw earlier, our oxygen has obviously 2 other electrons, which are core electrons, again, not involved here, while our fluorine also has 2 other core electrons that are not involved. So if we draw the Lewis structure for water, here again is 2 ways that you can sort of represent that. And as we see here on the bottom, first off though, if we look over here, again, you can show all the electrons as dots. And again, you can show the bonding electrons with the lines if you would like to represent it that way. But just like fluorine, the sharing of electrons are occurring here. So the oxygen in this case is actually sharing an electron with both hydrogens, 1 hydrogen electron in each. And by doing so, what happens with our oxygen, again, it's able to achieve that magical number in bonding, which is 8 electrons around it. So as you can see there in the blue circle on the bottom, the oxygen has 8 electrons around it. While each of the hydrogens here, by sharing with oxygen those electrons, are able to achieve 2 electrons in each of the hydrogens. And as we talked about earlier, that essentially is all hydrogen needs to get to helium, and it's perfectly happy here. So again, sort of magical numbers here as we're drawing, and what you always want to sort of achieve in most cases. We will talk about some exceptions, obviously, but you want to achieve 8 for pretty much everybody, and you want to achieve 2 for hydrogen and no more than 2 for hydrogen. And that brings us to 2 really important rules when we talk about bonding. And obviously the 8 is that number that keeps coming up. And that 8 is what is referred to as the Octet Rule. And the Octet Rule basically means that everybody except for hydrogen will continue to make bonds until they get 8 valence electrons around them. And they do that by sharing those electrons through covalent bonding. That could be, as we'll see, a single bond, could be a double bond, could be a triple bond to do that. But there's some aspect of sharing that allows both of those atoms to achieve that octet rule and 8 electrons. Again, the exception is hydrogen, which only needs 2. And again, that is sometimes referred to as the duet rule. Again, that gets hydrogen to move forward to helium, which again is that first noble gas that basically comes about. Now, let's talk about the different types of bonds that we see when we draw these covalent compounds. A single bond can be represented as we've been doing here, and we see on top there, you could represent a single covalent bond by 2 electrons being shared, like we see in the middle of the fluorine there, 2 dots. Or again, you can draw the line to represent that single bond. As you can see here, one line represents 2 dots are a pair of electrons. When we make a double bond, that is the sharing of 2 pairs of electrons, and that's represented by 2 lines. So in the case of CO2, it actually has double bonds on both sides. And each of these double bonds are represented by 2 lines. Each of those lines represents, again, a pair of electrons, which we see here. That means that for those 2 lines, there would be 2 pairs of electrons being shared, or 4 total electrons being shared between them. And in the case of carbon, as you can see, by making a double bond on each side, in the red circle, carbon's able to achieve 2, 4, 6, 8 electrons. And the oxygens on each side, by making that double bond with the carbon, is able to achieve also 2, 4, 6, 8 electrons. And again, everybody is extremely happy in that case. Everybody has essentially met the octet rule. And essentially what that really means is it moves everybody forward to the noble gas that comes right after them on the periodic table. Any questions on that there? We also have a triple bond, so like nitrogen here as well, forms a triple bond. And this is ethine that also forms a triple bond. And in a triple bond, it's represented by 3 lines. Each of those lines represents a pair of electron or 2 dots. So if we look in the middle here, 2, 4, 6 electrons. So 2, 4, 6 electrons are 3 electron pairs. And that's needed for each of these nitrogens here. So each of these nitrogens here, by sharing those electrons, they are each able to achieve 8 electrons around it, and again, makes them very happy. Same thing happens on the bottom there. The carbons need to make a triple bond with each other. And when they make a triple bond with each other, each of the carbons are able to achieve 8 valence electrons as they're sharing electrons there with the hydrogen. And each of these hydrogens also gets to 2 again by sharing electrons with the carbon. That hydrogen has 2. And by sharing electrons with the carbon on that side, that hydrogen also has 2 electrons in it. So again, everybody's perfectly good there. Hydrogens both got to 2 electrons. both of the carbons got to 8 electrons when we look at it. Any question on bonds or ways to represent bonds? So when we do have sharing of electrons, as I mentioned before, that sharing of electrons may be equal, or it may be unequal. So when we have sharing of electrons, one of those two things are going to happen. Either we'll have equal sharing of electrons or unequal sharing of electrons. And what that's going to create is really two different types of covalent compounds, or two types of covalent bonds is a better way of saying that. And really the thing that helps us determine, how those electrons are going to be shared within a bond is electronegativity. So if you remember, we did talk about, when we talked about electron periodic table trends, we talked about electronegativity. And again, a reminder, we'll see it here in a bit again. It increases as you go to the right and up, decreases as you go down. Fluorine is actually the most electronegative element that you could have. And electronegativity, as we talked about last time, is the ability of an atom to bring electrons towards itself. So obviously it increases as we go up to the right, as those guys pretty much like to hang on to electrons and gain electrons. So electronegativity helps us determine the difference between a covalent bond and an ionic bond. And we can also use electronegativity to help us determine that. Depending on the difference in electronegativity, we may have an ionic bond form versus a covalent bond. Now, when we take something like H2 that we saw earlier, when we have H2, because they're both hydrogen, obviously the attraction of those electrons to each of the atoms there in that bond is going to be relatively equal to each other, which if I just draw some really bad electron sort of density, just kind of looks like I'm drawing red on the screen, which you might be right, I am. And what we would expect to see is the electron density to be fairly equally spread out between the two atoms. And what that would imply is we would end up with some equal sharing of those electrons. Same thing's going to happen with our fluorine. Again, I'll draw it maybe like this, a little easier to see. Kind of equal sharing of those electrons between the two fluorines, as the electrons would fill an equal pool one way versus the other. And when we do get that kind of equal sharing of electrons, that is what is referred to as a nonpolar bond. So when we have equal sharing of electrons, that is what is known as a nonpolar covalent bond. Most people will just call it a nonpolar bond. So most people will just call it a nonpolar bond. And that is when we get basically electrons that are hanging out together, pretty much equally sharing those electrons. Now, what happens when we actually kind of take a bond like HF? Now, when we take HF, the electrons will no longer be shared equally between the hydrogen and the fluorine. One major reason is, there are different elements, so they have different periodic sort of trends, right, and properties. But there's also a difference in electronegativity. So if you remember, as I just mentioned, fluorine is the most electronegative element you could have. And obviously it is more electronegative than the hydrogen. So what we would expect to happen in the case of hydrogen and fluorine is we would expect a lot more of the electrons to be hanging out kind of towards the fluorine side versus the hydrogen side. And that also creates, as we will see, an important relationship between those two elements in that bond. Because all the electrons are pretty much hanging out over here on the fluorine side. The fluorine side is going to actually end up being more negative because it kind of has this buildup of electrons heading towards it. And it becomes what is known as partially negative. That's a delta symbol. Well, the hydrogen, which is losing those electrons, not really losing them, but they're moving towards fluorine, is going to become partially positively charged. And that's delta positive is what that little symbol is. So in a bond such as this, the atoms in the bonds create sort of partially positive charges and partially negative charges that occur. And another way that we can represent that is with an arrow, and these are sometimes referred to as dipole arrows. And the arrow points to the side that's more electronegative, and the back end usually will have almost like a plus sign built into it, and that's the side that's more positive. So we could draw this arrow again pointing to the more negative side of the bond, and the one that kind of looks like a plus sign on the arrow is at the more positive side in the bond. And this type of bond where we have unequal sharing of electrons is what is referred to as a polar covalent bond, but kind of like the nonpolar bond, most people will leave out the covalent part and really just call it a polar bond. So we really have two types of covalent bonds that occur. One where we share the electrons equally, and that's what's referred to as a nonpolar bond. And one where we have unequal sharing like we do here with the H and the F, and that is what is referred to as a polar bond. Any questions on that there? Here's a much maybe better way of showing it or drawing it. So again, if that pink is sort of the smear of electron density, again, you can see more of the electrons are hanging out towards that fluorine side is going to make it more negative, and the hydrogen is going to become kind of more positive as those electrons move towards the fluorine. And it does create these partially positive side and partially negative side. So an important thing to realize, why do we call it a partially positive charge and a partially negative charge rather than what we see in an ionic compound where something gains a full positive charge and a full negative charge? And that is because of the type of bonding that's occurring here. Although the electrons are not being shared equally, there is some aspect of sharing that's going on here. So because there's some aspect of sharing, what that means is those electrons have not been fully transferred from one side to the next. And because they are sharing it, that's why they are only positively partially positive on one side and partially negative on the other side. And that's different than in an ionic compound where we have a full transfer of electrons from the metal to the nonmetal. And because we get the full transfer of electrons that occurs, the metal gets a full positive charge, if you want to think about it that way, and the nonmetal gets a full negative charge because of that complete transfer of electrons. So when we think about sort of the three types of bonding that we talked about, there's sort of an arrangement as to how we can look at them. And let me see where I can do that here. Let me do it. Let me actually do it here. I'll try to squeeze it in here. So on one end of the extreme, we have an ionic bond. And as we talked about, that is between a metal and a nonmetal, where we have a transfer of electrons from the metal to the nonmetal, creating a cation that's positively charged and an anion that is negatively charged. No sharing of electrons. Again, what holds that together is that electrostatic attraction. So again, this would be an example like sodium chloride that we saw, any of those type of ionic sort of guys there, metal and non-metal comes together. Sort of on the other end of the extreme, we have a nonpolar covalent bond. And that is between two nonmetals where we have equal sharing of electrons. And that would be something like what we saw before, like H2 or F2. So let me just see your question there. Yeah, we're going to actually, as soon as we're done on this slide, we're going to get into how you can kind of really determine if you're going to get that unequal sharing of electrons or sort of the equal sharing of electrons. So in about a slide or two, we'll actually get into how you could kind of figure that out if you do have equal sharing or unequal sharing of electrons. The one thing that you will know for sure without the use of anything else is if you see a metal and a non-metal together, that's always going to be an ionic bond. So that's always going to be transfer of electron, no sharing. But we're going to talk about here in a couple of slides how you can kind of determine the level of sharing that you would expect when two atoms come together. And just to finish up this here, one extreme, our ionic bond, complete transfer of electrons. Other end of the extreme, we got perfectly equal sharing of electrons happening. And right dead in the middle there is really a polar covalent bond. So this is also two nonmetals. And again, here we have unequal sharing of electrons. An example would be right here, HF is an example of that. So on the right-hand side, they both have some level of sharing, equal and unequal sharing. And to the left, we have no sharing happening at all. And this is really our sort of three types of bonding that we come across: ionic bonding, polar covalent bonding, and nonpolar covalent bonding. Any questions on that? And again, we're going to get to your question, I think, here in a couple of slides. Okay. So to answer your question as to how do you know if you kind of put, these two elements together, would you expect those electrons to be shared equally or unequally? And it actually is electronegativity that we look at. So whenever we sort of have two elements coming together to form a bond, we can actually use electronegativity to help us determine what type of bond we would expect. Would we expect an ionic bond to form? Would we expect a polar covalent bond to form? Would we expect a nonpolar covalent bond to form? Again, a reminder that electronegativity is the ability of an atom to attract electrons towards itself in a chemical bond. Electronegativity of an element, again, is related to the electron affinity, which again is that energy change when an atom gains an electron. Generally increases as you go up and to the right on the periodic table, and also ionization energy. And remember that as you go up and to the right on the periodic table, elements have much higher ionization energy than if you go left and down on the periodic table. So fluorine has high electron affinity, high ionization energy, and has high, too many O's, I think, electronegativity. And sodium here has low electron affinity and low ionization energy and a low electronegativity. And again, if you just think about sort of their location on that periodic table, one's here and one's over here, they are pretty much on opposite sides of the periodic table. And again, would have obviously, as we can see, opposite sort of periodic trends. So a guy by the name of Pauling, a guy by the name of Pauling actually came up with a sort of method, a way of sort of assigning electronegativity values to elements. And the Pauling scale goes from 0 to 4. 0 being not very much electronegative. While 4 is the most electronegative. And you can actually use the values for each of the elements to determine whether or not you would expect the bond to be ionic, polar, or nonpolar. And we could do what is sometimes referred to as the difference in electronegativity values. The difference in electronegativity values are essentially you take the two values for each of the elements and you basically just subtract them and you'll get a number. And we're going to talk about that in just a second, what the number means and what numbers you should look for. But just again, a reminder, the general trend in electronegativity, and sometimes you don't actually need the scale to actually figure things out. You could just do it based on the general trend. Again, up and to the right in terms of electronegativity increases, left and down it decreases. So let's take a look at a chart here. This is a electronegativity chart, not from your book, but I believe you have a similar one in there. In terms of electronegativity. Just trying to move a couple of things out of the way here so I could see. There we go. All right, so as you can see on the left-hand side of this scale here where we have our metals, we have much lower numbers closer to 0, which again means they're not very electronegative. As we proceed up and to the right on the periodic table, we're getting towards 4. And again, here our fluorine being the most electronegative atom at a value of 4.0 is the highest value that we see. You'll also notice that if you look at the noble gases, which are not on this periodic table, so you can't really look at them, I suppose, but they don't really have values. That's because they're fine the way they are. They are chemically inert. So they pretty much have a value of like 0. They like don't want to change anything. They're perfectly fine the way they are. So that's why pretty much our electronegativity value kind of dead ends there at fluorine. Again, because if we go any further to the right, we already achieved the noble gases and they're perfectly happy the way they are. So there sort of is a general sort of scale that people use to determine what type of bond you would get based on the difference in electronegativity values. So if you do the difference in electronegativity values, and that difference is somewhere between 0 to 0.4, that usually will imply that the bond is nonpolar. And technically speaking, overall, it would be considered to be sharing those electrons equally. If you go from above 0.4, which I guess would be 0.5, right? We'll go 0.5. To below 2, that is some type of polar bond, which would imply unequal sharing of electrons. So above 0.4, which usually will be 0.5, so about 0.5 to just below 2, not 2, would usually indicate a polar bond. And if you get somewhere above 2, it would indicate an ionic bond has happened. So these sort of guys here is a good key. You do need to know this. This can help you determine what type of bond you would expect when you put two things together. Does it work perfectly on everything? It doesn't. But in general, those are usually the breakdowns that most books and most people will use to sort of figure these things out. So let's take a look at what we saw on the previous slide or a couple of slides ago when we were talking about the 3 different types of bonding. If you remember, at one extreme, we had our sodium chloride, right? And if we look up the value for sodium, it's 0.9. We look up the value for chlorine, it is 3. So if we take the difference in electronegativity, just take the bigger number minus the smaller. That's a lot of math there, but I'm going to go with 2.1 as the difference. 2.1 is above 2, and as we know and as we would expect, this would be an ionic bond. Now, if we go to the other side that we were looking at, where we had H2, right? H is 2.1, H here is 2.1. If we do the difference in electronegativity for this guy, 2.1 minus 2.1 gives us 0. 0 obviously is between 0 and 0.4. This is a nonpolar bond. And when you actually do get a difference in electronegativity of exactly 0, it is technically a nonpolar bond, but some people also classify this type of bond as what they call a pure covalent bond. And a pure covalent bond, which is, again, just another sort of word for nonpolar bond, it is still a nonpolar bond, is really when you achieve sort of perfect equal sharing of electrons. Now, if we look at HF, which is the other one that we had up there, hydrogen is 2.1, fluorine is 4. So if we do the difference in electronegativity, that is 4 minus 2.1, and I want to say that's 1.9 in terms of the difference when you subtract them. And 1.9 is just below 2, and based on our scale, that would tell us this is a polar bond. So we can use the differences in electronegativity, a chart such as this, to determine whether or not we would expect the bond to be polar, nonpolar, or an ionic bond to occur. Any questions on how to use this type of table here? Now, let's talk about a couple other sort of examples of using this table. For example, let's say we took the bond between carbon and hydrogen. Carbon on the periodic table there is 2.5 and 2.1. So the difference in electronegativity is 2.5 minus 2.1 gives us 0.4. 0.4, as you can see, is the top part of the scale that's considered nonpolar. So the carbon-hydrogen bond is considered nonpolar because of that 0.4. And really, to be truthfully honest, probably why the cutoff there is at 0.4, because all organic molecules are basically carbons and hydrogens, and they're nonpolar. So I guess if we didn't have that cutoff to call it nonpolar, there would be no organic chemistry. So the carbon-hydrogen bond is a nonpolar bond. Now, this also brings up a good point if you think about the difference in electronegativity that we see with our H2 and also our CH. They are both considered nonpolar bonds. One has a difference in electronegativity of 0, which would imply perfect equal sharing of those electrons, while the other actually has a difference in electronegativity of 0.4, which is still considered a nonpolar bond, still considered to share the electrons equally. But in reality, these electrons are really not being shared perfectly equal in the case of CH. In the case of CH, the electrons are just slightly heading towards the carbon side, right? The carbon being more electronegative in this case, but it's not to an extent where we do get that sort of separation of charge that occurs. So it's not to an extent where we do get the partially positive side, partially negative side. But in reality, because the difference is 0.4, they are not perfectly sharing those electrons. There is some aspect of some unequal sharing electrons, but it hasn't reached the level where it would be considered a polar bond. So it's still considered a nonpolar bond. And again, that's different than our H2, where we would assume that it is like perfect equal sharing of electrons. So why don't we take a look at a couple here. Let's say we had a bond between carbon and oxygen. Is it polar, nonpolar, or ionic? A bond between carbon and sulfur, and a bond between calcium and oxygen. So why don't you take a look at that does look like carbon as well. I guess if I put an A there, that becomes calcium. Better. All right. So take a second or two, figure out, are these bonds polar, nonpolar, or ionic? Okay, so let's take a look. So let's start with the carbon and the oxygen. Carbon being 2.5, oxygen being 3.5. So if we do the difference in electronegativity, that's going to give us 3.5 minus 2.5, which is 1. So that definitely puts us in the polar range. So we would expect this bond to be a polar covalent bond. Let's actually go to the other side here. Let's go to calcium. Calcium and oxygen. Calcium is 1.0. Oxygen, again, is 3.5. So when we do the difference in electronegativity, that is 3.5 minus 1. It says 2.5. 2.5 obviously is above 2, and we would expect this to be an ionic bond, as we know. And as I mentioned earlier, you really don't even need the values for electronegativity to determine that. As soon as you see calcium's a metal and oxygen's a non-metal, it is a pretty safe bet to go with it be an ionic bond. So you really don't even need it for ionic bonds, but they do have sort of the scale there. Let's take a look at carbon and sulfur. Carbon is 2.5. And sulfur is 2.5. So the difference in electronegativity obviously is 2.5 minus 2.5. That equals 0. And that 0 means that we're actually here. We're in a nonpolar bond in this case. So this brings up a really important sort of point when we talk about electronegativity. And that first point is, if you have two of the same elements that are nonmetals, it is a pretty safe bet that it's going to be a nonpolar bond. So you don't have to necessarily worry about calculating the electronegativity difference. You should expect it to be a nonpolar bond in that particular case. Now, if you have a metal and a nonmetal, as we were just talking about, you pretty much don't need the values either, because you should know that it's an ionic bond in that case. Now, this also brings up a good point that if you have two nonmetals and they are different, it may be a polar bond in a lot of cases, but it could necessarily be a nonpolar bond like what we have here with carbon and sulfur. The reason why it's a nonpolar bond in this case is it has to do really with their location on the periodic table. Although carbon is higher up on the periodic table. Sulfur is further to the right on the periodic table. They essentially cancel each other out in terms of their effect. This is what is sometimes referred to as the diagonal rule. So they are diagonal on the periodic table. So although one is higher up, the other one is further to the right. So they essentially will cancel out their differences. We also see that here if you look at nitrogen and chlorine. Again, diagonal of each other. They essentially have the same electronegativity. Again, you see that in a few different places as you look on the periodic table. Iodine and sulfur have 2.5 each, so they're diagonal of each other. So there's that diagonal relationship that we constantly see as well. Boron and As also have that diagonal relationship. So it is definitely possible to have two elements that are different that actually can, like we see here with carbon and sulfur, end up being nonpolar because of their relationship or sort of where they sit on the periodic table. Any questions on how to use a table such as this? It would obviously be provided for you if you needed it. If it's not provided for you, that means that you can, in general, just use the general trend in electronegativity to determine whether or not a bond would be polar or nonpolar. And what that means is, for example, if you were not given this table of values and you had something like carbon and oxygen like we had previously, and you wanted to determine is that bond polar or nonpolar, you actually could just use the periodic table and help you decide that. So when we look at the periodic table between these two elements, we see that carbon is right here and oxygen is right here. They are in the same period on the periodic table. And if you remember, the general trend in electronegativity is it increases as you go to the right, which means we see that oxygen is further to the right in that period than carbon is. That would tell you that those electrons are not going to be shared equally. That would also tell you that the oxygen is more electronegative than the carbon, and you would actually not even need the value there. So you wouldn't actually need the numbers to figure that out. You could do it just based on their position on the periodic table. You could simply draw the dipole arrow just like this, heading towards the oxygen, which is more electronegative than the carbon. Same thing if you were comparing, for example, oxygen and sulfur. Oxygen is here, obviously. Sulfur is right about here. And what we see is sulfur is lower on the periodic table than oxygen. And the other trend we know about electronegativity is as you go down, it decreases. So without having the numbers there, we would know that sulfur should be less electronegative than oxygen. And we should know that this will be a polar bond because of that. And again, we could draw the arrow pointing towards the oxygen, which would be more electronegative. That, by the way, should be a straight arrow. That is definitely a badly drawn straight arrow, but it should be a straight arrow pointing to the more electronegative. So if you're not given the values, that means you probably can just use the periodic table and the general trend in electronegativity to determine if the bond's going to be polar or nonpolar, especially when we're dealing with our nonmetals and nonmetals. Any questions on that? So just to finish up on this topic here, since we're getting to the end here of lecture, a very important thing to keep in mind what we're talking about here with electronegativity. So in general, in most cases, probably 98% of the time, if we are using the electronegativity values, what we are really trying to determine is whether or not the individual bond, so the bond between, say, this atom and this atom, the bond between those two atoms, is that bond going to be polar, nonpolar, or even ionic if you need to use those values. We are not talking about the entire molecule as a whole. in most cases. We'll talk about some cases where we are, but in most cases, we're not talking about the molecule as a whole. Is it polar or nonpolar? So sometimes what we're referring to here is what is referred to as bond polarity. And bond polarity is simply that if you took these two elements, these two atoms of these elements, and you put them together, would you expect those electrons to be shared first off? And would you expect those electrons to be shared equally or unequally? And that's truly what we use really electronegativity for, is to determine individual bond polarity. Is it polar or nonpolar? Any questions on how to do that there? Okay, so just to finish up, again, as we saw, widely differences in electronegativity values will lead us from ionic bonds to covalent bonds. And again, because everybody is near each other in terms of nonmetals, the best they could do in terms of electronegativity is, since they all pretty much want electrons, the best they could do is compromise and go, we'll share electrons. And again, when we get a metal and a non-metal together, they're on opposite sides of the periodic table. So again, in terms of electronegativity, our metals are like, I don't really care about electrons. I don't want to bring them towards myself, where our non-metals want to bring those electrons towards themselves. So when we get those metals and non-metals together, we get that transfer of electron versus the sharing of electron that we see. All right. We will stop here today. Any questions on anything we talked about today in lecture? Okay, so coming up in lab today is actually study assignment A. So that is again found in your lab manual, in the back of your lab manual. So there's all the experiments, and then I think that's where the study assignments sort of come into play. And it's about significant figures, conversion, density. So we'll take a little bit of the time, and we'll talk about those things just to make sure, again, everybody's on the same page in terms of sort of significant figures and calculations with significant figures, a little bit about conversions, and a little bit about density and some temperature conversion. So we'll lecture a little bit on that stuff, and then you can obviously go and work on your study assignment A. Any questions on anything? Okay, so see everybody about 9:45-ish there in the lab lecture. If you didn't type here in the chat box, please make sure you do that before you take off. And I'll see everybody in about 20.